This video is entitled Differentials. Now you may recall differentials in Calculus 1 or calculus of a single variable as dy equals f prime of x dx, and that's what we use for single variable integration. And then an application of this differential was used to approximate a function change in y. So you're using a differential to approximate some change in function y, with delta x being the change in x and delta y being the change of y. So delta y is actually calculated as f of x plus delta x minus f of x. But then the dy approximates that delta y, whereas dx equals exactly delta x because that's the independent variable. All right, so we looked at some examples when we did that with if measuring devices were off a little bit, then how much would that affect the overall measurement of something like volume or area or something like that. So it's okay if you've forgotten that because you wouldn't have likely used that in Cal 2 anyway. Now we're going to expand this a little bit further, since now we have the idea of a dependent variable being a function of two or more variables. Now we're only going to use two variables here, thank goodness, or we get a lot messier, but we might use more than two, but as far as doing this kind of application, we only want two variables. But you can expand this total differential concept here. So now, but this is where both x and y are independent variables. So dx equals delta x and dy equals delta y. Therefore, then the actual delta z function, the true change in z based on f of x and y, would be your second point value for z. When you put in the delta x, you put in the delta y and evaluate the function, minus the original value of the function. That gives you your delta z. But in your total differential form here, dz, I'll skip over to this part right here. It's just partial derivative notation differently, but it's your partial respect to x dx, and then plus partial of y respect to y dy. So you could expand this. Let's say if w was a function of x, y, and z. So you'd have fx dx, fy dy plus fz dz. So let's just take a look at this. Is just the total differential, then we'll look at some applications coming up. In fact, here's what I was just talking about. This number 10 right here has more than two variables, independent variables. Now this one's not too bad. You got z as a function of x and y. So that means we want the x partial of this, which will be bring the 4 down, makes that 8x cubed y, minus bring the 2 down, 16y cubed. So right here we have 8x cubed y minus 16xy cubed dx. And then the y partial of this would be 2x to the 4th minus 24x squared y squared. dy. So that's just your general differential form. And here's number 10, where it's a function of three variables. The partial of this respect to x would be 2xy z squared. There's no x here, so that will be 0. It goes away. So here it is, 2xy z squared dx. The next one, the derivative of y respect to y, would be 1. So it's x squared y squared. Plus the derivative sine of yz would be cosine of yz times the derivative of the inside with respect to y, which will be z, because the derivative of y would be 1. So that's where that z is coming from right there. So I realize the section before these, maybe not in every textbook, but the one I'm referencing here is the partial derivatives. So I'm assuming this is still kind of a fairly new idea for us. So it's cosine of yz times z, which the z could have been in front of the cosine, of course. All that in parentheses dy. Now this one, respect to z, is going to be 2x squared yz plus cosine yz, and then the derivative of yz with respect to z, which will just be y, because the derivative of z will be 1. All right. Now we're actually going to use this to approximate a change in a function value, and we're going to also calculate the actual change. So I would make sure clearly worded, which is your starting and which is your finishing point. But we're assuming we're going from f of 2, 1 to 2.1, 1.05, and keep in mind that these values for x and y could decrease. It doesn't. The second point doesn't have to be larger x's and y's than the first point. So the actual change, so you would just take f of 2.1, 1.05, and plug it in this function. I'm just mentioning over here that I'm in radian mode. So everywhere there's an x, I'm putting in 2.1. And then where's y? I put in 1.05. So right here, x is 2.1. So it's 2.01 cosine of 1.05 minus 2, which is that cosine of 1, which is the initial point. So it's like terminal point minus initial point. Kind of using, vector terminology there, but maybe that makes it easier to understand. And I just chose 4 decimal places here. Negative 0.0357. Now the differential then would be, so it would be the derivative of this function with respect to x, which would just be cosine of y. So it's cosine of y dx. And then the derivative of this same thing with respect to y, the x will sit there because it's multiplied. Then the derivative of cosine of y would be negative sine of y. So it makes it negative x sine of y dy. Now dx and dy represent the numerical values for the change in x and the change in y. So if you're going from 2 to 2.1, I just subtracted right there. That means it increased by positive 1. See, like I said before, these could decrease. And then from 1 to 1.05 is an increase of 0.05. So that's the values that we will plug in for dx and dy. So see, there's the 0.1 going in there for the dx. Here's the 0.05 going in for the dy. So x is 1, so I have cosine of y, y is 1, excuse me, x is 2. So I have cosine of 1 here, radians. And then over here I have negative x sine of y, so it's negative 2 sine of 1. And then 0.05. And put this in the calculator, I get negative 0.0301. Now the idea here is that the dz is supposed to be close to the delta z. Now I still consider that close enough. Sometimes you'll see them a lot closer because dz is actually approximating delta z. That's not too bad, and obviously the fewer number of decimal places, it's better. But it's okay. Obviously you just don't want to be way far off. If you got negative 0.0357 here and you got like negative 4.2 down here, then you would know that you were really, really far off and something's wrong in your calculation. But that's close enough. And there we go. And here's another one. So our function basically is the square root of x squared plus y squared, which is the same thing as to the 1/2 power, of course. Now we're going so that's what I was talking about. I'd make this a lot more clear if I was giving this problem. From 7.3 to 7.1, 2.7. So notice that x is increasing, but y is decreasing. So what that means is the dx is going to be a positive number, and the dy will be a negative number. So to go from 7 to 7.1, all you got to do is take 7.1 minus 7 is positive 0.1. Then if you take 2.7 minus 3, you get negative 0.3 because y decreased. So here's the delta z. We calculate f of the second point minus f of the first point. So it's f of 7.1 comma 2.7 minus f of 7 comma 3. And I did that one step in the calculator. So it's the square root, going right back up here, of 7.1 squared plus 2.7 squared, minus the square root of 7 squared plus 3 squared, and I got negative 0.0197. There we go. Now let's look at the total differential. So we take the derivative. So you bring that with respect to x, 1/2, leave the inside alone, decrease the power to negative 1/2. Then we take the derivative of the inside with respect to x. That'll be 2x. I just canceled those 2's there because I could. And then there's your dx. And then over here it's essentially the same, except when you take the derivative of the inside with respect to y, you're going to get 2y. 2's cancel. So now I come down here, and your starting point always represents your x and y when you do this. 7 squared plus 3 squared to the negative 1/2 power. 7 squared plus 3 squared is 58. So over in the calculator, I just went 7 divided by 58, square root of 58, because obviously the negative 1/2 makes it go down. So it's 7 divided by square root of 58 times 0.1. So there's your 0.1 representing your dx. And then same thing over here, we're going to have dividing by the square root of 58, except we have 3 divided by the square root of 58, and then times negative 0.3. And we get an answer of negative 0.0263. So once again, that's not super close, but it's not far enough of a difference to make us be concerned about it. You know, it's kind of in the same general ballpark. Let's take a look at this next one. So some of you future electrical engineers might find this one interesting. It's a little bit messy. Maybe not a great one for an exam, but a good one to take a look at. This formula, this resistance formula of resistors connected in parallel. So basically you're saying R is a function of R1 and R2. So R1 is increased from 10 ohms to 10.5 ohms, and R2 is decreased from 15 ohms to 13 ohms. Now to make this a little easier to work with, the first thing I'm doing is, because you notice I don't have like the independent variable is not isolated by itself, it's 1 over that variable. So I got to do a little algebra here because I want it just to be R on the left side, not 1 over R. I could work with it that way, but I don't want to. It's easier not to. So I just multiplied everything through by the least common multiple, which is those 3 values, and got to this form right here. So I kind of cleared out the fractions. Then I factored out an R on the right side, like so, and then divided by what I factored out right here. So R is the same thing as R1 times R2 divided by R1 plus R2. I decided at this point that it was a little confusing to be working with R, R1, R2, maybe algebraically. So I decided to turn this into X, Y, and Z. So I'm defining Z as R, and then X as R1, and Y as R2. So we would now have, so this function right here in red comes down here and would look like this if I change it according to those substitutions right there. So now we have Z equals XY divided by X plus Y. Now back up here, it said R1 increased from 10 to 10.5. So R1 is X now in our world. So that's an increase. So it's positive 0.5 represents an increase. R2 is decreased from 15 to 13. So it went down 2. So dy then here is negative 2. So now we can solve it. So it looks like I chose to do the differential. Okay, I'm not sure if it didn't even ask for the approximate the rate of the change. Approximate means the differential. It looks like at the very end I went ahead and did do the delta z, the actual change, but it wasn't asking for it in the instructions. So that's why I started with the differential this time. So we've got quotient rule. Bottom times the derivative of the top with respect to x would just be a bottom here. Derivative of the top would be y minus the top xy times the derivative of the bottom with respect to x would just be 1. So there's that one over the denominator squared. So I kind of didn't have to do this, but I saw quickly that a couple of these terms were going to cancel, so I went ahead and did that. No need to expand out that binomial, but I just simplified it into y squared over x plus y squared. But I could have worked with it in this form too. Quotient rule again, except this time the derivative of the top with respect to y will be x, right there, minus xy times the derivative of the bottom then with respect to y would also be 1. That also simplifies and leaves x squared on the top. So now I come down here to calculate the total differential. So, and here's I've just copied all the values from earlier there. So R1 and R2 were 10 and 15. So they're now x and y. And we already have the dx and the dy. I looked at that. So we've got, just plug them in. So we got 15 squared over 10 plus 15 squared times 0.5 plus the 10 squared here for x over 10 plus 15 squared times negative 2. And I got negative 0.14 ohms. And I guess I just drew the ohm symbol for no particular reason. And then down here, even though it didn't ask for it, I took the original function and took the second point right here, 10.5 comma 13, and subtracted off the first point where it was just 10 comma 15 and got negative 0.19 ohms. So that negative 0.14 ohms was a pretty decent approximation for negative 0.19 ohms. All right, let's look at a measurement error problem here. The possible error involved in measuring each dimension of a right circular cylinder is plus and minus 0.05 centimeters. The radius is 3 and the height is 10. Approximate the propagated error and the relative error and the calculated volume of the symbol. All right, now this is using terminology back from the section on the differentials in Cal 1. The propagated error is the same thing as finding the differential. That's the differential. Because in other words, we're saying that we can't really get the exact value here. So we're going to use the differential to get the approximate the exact value. Now I would not expect you to know this formula on the right. If any kind of problem like that I use that would use some sort of geometric formula like that, I would provide that formula. So propagated error is strictly the differential because that's your approximated error. Now what relative error was defined at back then, it's the same now, is you take, actually I like percentage error better. When you see down here, when I finish I'll show you percent error. That means you take your propagated error and you divide it by the actual volume by putting these original numbers in there. So you're trying to figure out as a percentage what kind of error could you have in the measurement overall, essentially. That's what kind of, could we possibly have a 3% error or whatever, and then I guess it's up to someone to decide what's considered, an acceptable range of error or not. But Okay, so I took these the derivatives v as a function of r and h. So I took them as, v sub r, v sub h for partial derivative notation. So the derivative with respect to r, you just take the r squared would be 2r. So it's 2 pi rh. And then v of h would be pi r squared. And so the VH then would be the derivative of h would be 1, so it would just leave pi r squared. And it's very common for these kind of problems. So it's giving you the measure in each dimension. It's the same. So yeah, that makes sense. So if you're using the same measuring device, you would expect the possible error of measurement to be the same. So that makes both dr and dh be plus or minus 0.05. And that makes sense. So they're both the same values. So the propagated error, the differential dV, then would be v. Basically, it's vr dr plus vh dh. So we're putting in 3 for radius and 10 for the height. So 2 pi 3 times 10, because it's right here, pi rh, times plus and minus 0.05, plus pi times 3 squared, there's no h variable there, times plus and minus 0.05. And that's approximately plus or minus 10.84 cubic centimeters. That means the relative error would be the 10.84 divided by the volume that you would get from using that device. So it was pi r squared h. So pi times 3 squared times 10, so you divide that, plus or minus 0.0383. Some books don't necessarily use plus and minus. They just sort of take it as a given. They just use, with the positive, meaning knowing you can be to either side. I kind of like the plus and minus, though, because it's showing you that, we're saying we could be, below the actual amount a little bit or above the actual amount a little bit. Positive may make you think that you can only overestimate the answer, and that's not true. Yeah, so percent error is it's just the relative error doesn't make sense because it really doesn't have any units or anything, because the cubic whatever would cancel out when you divide it. But as soon as you make it as a percent, you can kind of get a feel for it. So you multiply it by 100. So now we're saying we could be off by 3.83% of the total volume, in other words. A little up to that much below or above it. So, all right. Let's take a look at another one here. Right circular cone. Radius and height are measured to be 2 and 5. So radius is 2, height is 5. Possible measurement error is 1/32 inch. Approximate the maximum possible error in the computation. That's the same as the propagated error. I just used a little bit different wording there. And the volume and the percent error. So once again, you would be given a formula like this, and then it's up to you to get the derivatives from there. So VR would be the derivative would be 2r, bring the 2 down, 2/3 pi rh. And then VH, the derivative with respect to x, would be 1/3 pi r squared. R is 2 is h and 5. dr and dh are both plus and minus 1/32. So here's your dV, would be VR dr plus VH dh. So we're using this attached with dr. So yeah, your dr and your dh then are both plus and minus 1/32. So it's 2/3 pi 2 times 5. And then over here we have 1/3 pi r squared, so no h. So it's 1/3 pi times 2 squared, because that's what r is. And I get, I think decimal would have been fine here. I don't know why I came up with the exact answer there. I don't know. But it turned out being plus or minus pi over 4. I think decimal would have been all right. But the fact that I had a pi in there and left it as pi enabled me to cancel the pi in the next step of finding the percent error. But that was not necessary. You still could have done it with just decimals. And there's the original. So we're trying to look at the original volume, 1/3 pi r squared h. So since that has a pi, I just cancel the pi's. So it ends up being, divide by 1/3. So you can do the math any way you want. But what happens here, the numerical calculations, the 4 comes down and you would divide by 1/3. That's the same thing as multiplying by 3. So the 3 is on top, and you have 2 squared 5 on the bottom. I didn't even write plus and minus on that. I guess I forgot to put that in the answer, but that's okay. It's not the end of the world if it's not there. But it would be plus and minus 3.75%. Possibly the entire volume being off somewhere in that range. So, well, all right. That concludes this video on differentials.